All right, so let's talk about what happens after halfway to the equivalency point. So we call this sort of the later buffering region after we're halfway, but before we reach the equivalency point. This is when the concentration of the A minus is greater than the HA. So essentially the concentration of the base is greater than the concentration of the acid. So in this region, we're adding more sodium hydroxide there. The hydroxide is combining with the hydrogen and making that A minus. Now, once again, this is still a buffer region. This is still a buffer because we do have the conjugate base and we also have the weak acid in the solution. So still a buffer, even though you're getting a little bit more basic as we go. But during this region, this region right here, the overall pH isn't changing a whole lot because you're in that buffering region. You would calculate this exactly the same way as we've been practicing. So do stoic first, and then do the equilibrium. Now, once again, still, we do this the same way. This is still in that later change. We're still adding that hydroxide. We're still making water and A minus. Now let's talk about what happens at the equivalency point. Now, when we're at the equivalence point, all of the acid has reacted. So if you look at a little diagram up here, all of the acid is gone. There's no HA left in the system. So we have only the conjugate base. So this is no longer an acid. Now, because it's only the conjugate base in the solution, it is the base. It is now a base equation. So if you look right here, this is now a KB. And then we have a little shortcut here where it's x squared divided by the concentration of the base, and AX is the OH minus. This all comes from a Quack table. So all this information comes from doing a Quack table. The hard part about this is what is the equation? That is the hardest part. If we kind of continue on here, you can see that um, that A minus is actually combining with water. It's ripping off a hydrogen, and you have a little bit of that HA left, and OH minus is made, which is how the base functions in the water. So essentially, when you reach the equivalency point, it is a saltwater solution. It is no longer an acid, it is now a saltwater solution. After the equivalency point, you got to do a little bit of stoic, but essentially the weak acid and the conjugate base no longer matter. You just have excess hydroxide ions, and so you just deal with them. You don't have to worry about anything else when you're doing anything with that equilibrium stuff. You don't have to do that at all. It's just stoic because you're just adding more hydroxide, and that's going to overpower everything. So before the equivalency point, we have this buffering region, which is after the equivalency point, right before the or after the, when we start, and before the equivalency point. We have halfway, which is a really important thing that comes up a lot. We have the equivalency point, and we have that after the equivalency point. Those are the certain areas. All right, so we're back and we're solving the last part of exercise 12 here. We still have the same information above. We have 50 milliliters of that 0.1 molar HCN with a Ka of 2.6 times 10 to the negative 10th, and we're titrating that with a 0.1 molar NaOH. And our job is to calculate the pH of this reaction. So this is after we've added some sodium hydroxide. So the first thing we need to do is stoic. So we're going to take that HCN, which is aqueous. We're going to add to that the hydroxide ion from the sodium hydroxide, but the sodium is not going to do anything. And that is going to make water, which is a liquid, plus that Cn minus aqueous, which is our conjugate base in the reaction. If we're doing stoic, it's a rice table. We said previously that we had um, in our stoic problems, we had 5 millimoles of HCN. So we have 50 milliliters times 0.1 molar. That is 5 millimoles of the hydroxide ion. This is 0, or we can just not care about it because it's the liquid. And then we have 0 of this. So this is 5 and this is 5, and it's a 1-to-1 mole ratio. So for this we no longer really have an excess or a limiting. They're just both limiting because they're in perfect proportions. Um, X is going to be 5 millimoles for this reaction. And if that's true, this is 0, and all of that has been converted into HCN and water. So we have 5 millimoles of the HCN. So that's pretty nice because we don't have to worry about, um, the HCN in the reaction. So we have just this in the reaction. It gets a little confusing though because um, we have only that base. So this is going to act like a base. So when we do the equilibrium stuff, we need to write it like a base. We need to write it like a base reaction, reacting with water, taking a hydrogen. Um, so it's going to look like this, and this is probably the hardest part. Cn minus is aqueous, and that's going to combine with water to be at equilibrium with OH minus aqueous plus HCN aqueous. So essentially what's happening is this HCN, once it's created, is going to rip a hydrogen off water, make the hydroxide, and it's the HCN. Now this can get confusing. Don't let this get confusing. This value is not this value. Don't do that to yourself. This is before equilibrium. This is after we've already produced this much. Now let's figure out how much hydroxide is formed from this base in the solution. It's not the amount of base added. Don't put that number there. You're going to get really, really wrong answers. Because this is no longer a ratio and a buffer region, we're no longer in the buffer region, we do need to have this in concentration though. So we want to make sure that we do that. We have 50 milliliters, 50 milliliters, we have 5 millimoles. So we have 100 milliliters total. So our initial concentration of this is 0.05 molarity. So you want to be really careful when you're doing that because it does need to be in molarity for this. H2O is not going to matter. We have 0 OH minus and 0 HCN once it reaches that equilibrium point. So this is going to be minus X, and plus X. So 0.05 minus X, X, and X. Now, this is a Kb because it's producing that hydroxide ion. So let's write out the Kb expression for this. We have Kb is equal to the concentration of the OH minus times the concentration of the HCN divided by the concentration of the Cn minus in the solution. Now this is a Kb. We're given in our problem Ka is 6.2 times 10 to the negative 10th. So we need to do that conversion between the two, where Ka times Kb is equal to 1.0 times 10 to the negative 14th. So we're just going to do that little calculation to find what Kb is. So we have 1 times 10 to the negative 14th divided by 6.2 times 10 to the negative 10th. We get 1.6 times 10 to the negative 5th for our Kb value. So now we're going to plug these numbers in. So we get 1.6 times 10 to the negative 5th is Kb. We get X and X divided by, this is going to be 0.05 minus X. We're going to say that this X is negligible because 0.05 is much greater than X. So it's negligible. All right, and then we get X to be, we're going to do 1.6 times 10 to the negative 5th times 0.05, square root of that answer, we get 8.9 times 10 to the negative fourth molarity. And then what is X equal to? This is where this is different. Everything else is H3O plus. Here, the X is equal to the concentration of the OH minus. So the first thing we're going to do is going to find POH. So to find POH, you would take the negative log of that. So negative log of 8.9 times 10 to the negative fourth. We get 3.05, which means that the pH is going to be equal to 14 minus 3.05, which is 10.95. So at the equivalency point is pretty basic, which is pretty typical for weak acid, strong base titrations because it's a saltwater solution, and that saltwater solution is basic. So that's our final answer. If we notice, our pH does go up the whole time it should. It starts off at a 5.1, 8.49, 9.21, and finally at the equivalency point, it is 10.95.